Some stars look like frozen metal and they should not exist. They break known physics by changing how matter organizes. Imagine a city-sized object glowing weakly in deep space. Astronomers call some of these objects strange stars. Finding one would rewrite dense matter physics and astrophysics. Under extreme pressure, neutrons break into free quarks. If strange quarks appear, the mix can become energetically favored. A strange star would be roughly 10 kilometers across and ultra-dense. So, a tiny, ultra-dense ball of quark matter is possible. Deep inside collapsed stellar cores, pressure reaches unimaginable levels. A strange quark star is a compact object made mostly of quarks. It matters because quark matter would change mass, size, and cooling. At roughly nuclear density, neutrons dissolve into up and down quarks. When strange quarks join, the mix can become energetically favored. That could make a star more compact and slightly smaller. A typical neutron star weighs about 1.5 suns. A strange star of that mass might shrink to about 10 kilometers radius. Its surface would be sharper and not covered by a normal crust. Some models predict smaller radii by a couple kilometers, so strange quark matter could make stars denser and smaller. After a supernova, a core collapses to extreme density and heat. This core may become a neutron star, spinning and glowing. A strange star could form if a seed of strange matter appears. That seed could come from collisions or from particle processes in the core. If the seed is stable, it converts the surrounding neutrons into quarks. The conversion spreads rapidly, like burning paper, across the star. Within seconds to minutes, the whole star could change its internal state. This process would release neutrinos and possibly a faint light show. One model estimates conversion timescales of order seconds to hours. Observationally, a sudden change in rotation or a neutrino burst could signal it. So formation may be fast, dramatic, and leave detectable traces. Astronomers look for small radii, odd cooling, and strange emission. Radius measurements come from X-rays and thermal modeling. Cooling depends on internal particles and how they carry heat. Quark matter allows fast cooling via direct Urca processes for neutrinos. A strange star might cool faster and appear dimmer than peers. Pulsar timing could reveal sudden glitches or unusual spin-down behavior. Gravitational waves from mergers could show a softer equation of state. G170,817 already set limits, ruling out some very soft models. A candidate would be compact, dim, and produce an unusual merger signal. So multiple signals together strengthen the case for exotic cores. There are other hypothetical compact objects, stranger than strange stars. Boson stars are made from a single quantum field, not fermions. They matter because they offer dark matter alternatives and novel gravity tests. Mechanically, scalar particles clump via gravity, forming stable, macroscopic balls. Boson star masses vary dramatically, from asteroid scales to many suns. A boson star of one solar mass would be diffuse, unlike neutron stars. Preon stars hypothesize even smaller building blocks, sitting at ultra-high density. Dark stars would interact weakly and glow only via annihilation processes. Finding any of these would force a rethink of particle physics, so the zoo of compact objects includes many plausible, exotic candidates. Some hybrids put a neutron star inside a giant star's envelope. These Thorne Żytkow objects look like bloated red supergiants from outside. They matter because they show how stars can host compact cores. Inside, exotic burning and accretion create unusual nucleosynthesis signatures. Electroweak stars are even stranger, using particle physics to resist collapse. Their cores would convert matter using electroweak interactions, releasing energy. Both types would show odd surface abundances and anomalous luminosities. An example candidate shows unusual elemental lines and unusual brightness. Detecting these would tie stellar evolution to exotic core physics. So hybrid stars teach us how extremes combine in surprising ways. The main barrier is our ignorance of matter at extreme densities. Quantum chromodynamics becomes nonlinear and hard to calculate directly. Laboratory experiments reach high temperature and lower densities, not core conditions. Lattice QCD helps, but it struggles with finite density regimes. The equation of state determines whether quark matter is stable or not. Observations of massive pulsars over two solar masses constrain soft equations. Those massive stars suggest matter resists collapse, limiting some exotic models. Still, uncertainties remain large and theory allows viable exotic phases. So the case for strange stars rests on delicate, ongoing physics work. Lately, new data have sharpened the debate and added surprises. NICER measured pulsar radii, giving tighter constraints on sizes. Gravitational waves from mergers provided independent pressure measurements. Some X-ray dim objects appear smaller, possibly too compact for neutrons. High-mass pulsars above two solar masses reject some soft equations. At the same time, some thermal spectra hint at unexpectedly small radii. Candidates remain controversial, and alternate explanations persist. Future missions and more merger detections will sharpen this picture, so the observational story is active, promising, and not settled. We began with stars that should not exist, and the possibility persists. Exploring them ties together extreme physics, observation, and imagination. If you enjoyed this curiosity, consider subscribing for more cosmic puzzles.